introduction, and thank you for the organizers for the invitation. And it's a pleasure to talk to you about the depth of anesthesia monitoring, possible future in this field from probabilistic to mechanism-based monitoring. I'm sure all of you are aware of current concepts of depth of anesthesia or hypnotic level of anesthesia monitoring. All these monitors which are available on the market at the moment are based on a common principle. It's not really a physiologic measure that we are following, it's a constructed index. So it's a general principle. You have physiologic signals being the EEG or the evoked potential as seen on the left side. These are recorded, there is some signal processing, and parameters are calculated. I like the comparison to an arterial line curve, which is a biological signal, and this can be recorded, and then there is some processing, filtering to get the signal properly designed, and you can calculate parameters being the top of this arterial line curve as the systolic pressure and the base as the diastolic. And you can, depending on the calculation algorithms, calculate several parameters from the EEG as well. The indices that we use at the moment go one step further. They integrate clinical assessment that has been performed during design of those, during the design studies, and by different statistical methods, these informations based on clinical assessment are combined to calculated parameters to produce an index which reflects the hypnotic level of anesthesia. So it's not really a physiologic measure. We started at that point for the probabilistic approach with the belief we teach our residents, we teach our fellows that you should not solely, exclusively rely on a new EEG-based parameter when you assess the level of anesthesia, and just you neglect or ignore all the parameters that's been used so far. And this is basically a study that we did in 6 European centers, and in different to other approaches where they compared standard clinical approach to EEG-based approach, we tried to integrate this information with EEG and standard monitoring. Now this is still the probabilistic approach, but this includes more information than EEG only. There's a wide range of anesthetics which were used, and we had this clinical pathway through anesthesia, induced after a period of awake signal. We induced loss of consciousness, then we maintained anesthesia until skin incision, and then we increased the level of anesthetic concentrations until burst suppression occurred in the EEG. After that, we decreased the level of anesthetics to a clinical level of anesthesia, and at the end of surgery, we performed this assessment for return of consciousness, being the ability of the patient to respond to command. Parameters were not only EEG-based parameters as seen here on the top, but there was an inclusion of standard monitoring, heart rate, blood pressure, difference between in and expiratory oxygen and anesthetic gas concentrations, a trend in mean arterial blood pressure, drug informations, and this is basically what we expect from a clinical anesthesiologist to integrate as a whole field of information. And using this set of data, we combine them, synchronize them time-wise, and build 2 classifiers, one for the separation of consciousness and unconsciousness, and one over the whole range of anesthesia. These two separate classifiers were combined to a single number, and it showed that we could show that such an approach provides a more precise information of the hypnotic level of anesthesia. There was a better separation between consciousness and unconsciousness, and also between different defined levels of anesthesia as compared to EEG only. So on the right-hand side, you see the information from the bispectral index monitor. On the left-hand side, with a very similar approach, also probabilistic, but including more parameters, you get a more precise information. Now, very recently, we completed a validation study of this monitor, still a probabilistic approach. The validation of the algorithm that has been developed was done in 3 German centers. Now, standard clinical practice, non-cardiac anesthesia, and the anesthesia multimodal indicator of consciousness, the AMIC, was used for that. These are the parameters which go into it. So it's an EEG-based parameter analysis. There's information about heart rate and blood pressure, about ventilation, drug information, calculated plasma concentration of propofol, volatile anesthetic concentration, and demographic data as well. And we showed that results are, in this validation study, are fairly similar to the one that have been shown in the design study. So there are minor differences, and we see that in particular in deep levels of anesthesia, the separation was not that well as it had been in the first study, but that was basically due to some study design issues, because in this study we were not allowed to target EEG burst suppression. Our ethics committee did not approve to that. And of course there is always a potential of limitation of machine learning, which was applied in the first study. So there is a risk of overfitting data to this design study. There is quite a good separation, a very good separation actually, between wakefulness and responsiveness during induction, but not at return of consciousness. And this fits quite well into observations that support the thesis that waking up from anesthesia is not the inverse of induction of anesthesia. And this is from an editorial from Max Kels and Jamie Slay, who separated this very well from each other and showed different pathways of waking up after anesthesia, which is definitely not the inverse of going into anesthesia. So you can wake up because the level of general anesthetics decreases. You can opiates and clonidine have an influence on it. There may be wakefulness driven by regain of consciousness as a reorganization of cortical structures, but there may be subcortical structures fastening or making return of consciousness on a different level, on a different systemic level. Now this strongly suggests that you have to look into mechanisms of consciousness if you want to measure it. And I'm sure all of you are aware of the overview article in Science about anesthesia-induced consciousness and the theory of cortical disintegration. And I want to go quickly through it. It has been shown that with the applied stimulus, there is a specific pathway of information over the cortex. And this means there is a signal input and there is a perception or a reaction to the signal input by primarily cortical perception areas. This is the information is transmitted to the front of the brain, and then there is a feedback loop to the back of the brain, which makes sure that the information is perceived. This has been shown in rats initially, and then later on with a similar approach in volunteers. Farrelly induced sedation in 11 volunteers, and his group used EEG and transcranial magnetic stimuli, analyzing 8 or 6 deeply sedated volunteers. They found a very similar reaction pattern to the transcranial magnetic stimulus. Now, transcranial magnetic stimulus induces electric activity in the cortex, and this activity is transferred in awake volunteers in a specific manner over the cortex. So there is a specific pathway which this electric activity follows. During midazolam-induced loss of consciousness, there was still a reaction, or there is still a reaction, as seen on the right-hand side, of the cortex to the stimulus, but this reaction remains mainly local. So it's not distributed over the surface of the cortex, and perception is not possible in this state. Now, this was a very first study with a stimulus. About at the same time, there was this groundbreaking Belgian study about the effect of Propofol on resting state functional connectivity during Propofol-induced unconsciousness. The study group from Liège was looking at 20 volunteers, and they induced Propofol target-controlled infusion until unconsciousness, and they analyzed functional MRI. Now, functional MRI reflects oxygen content of different areas of the brain, and the theory behind it is that there is an autoregulation and very active cortical fields or brain areas are reflected by a high oxygen content. And as a matter of fact, there is a significant change of very specific brain areas which are active and connected to each other if you induce unconsciousness by Propofol. And these fields, which are mainly reacting, are the so-called, it's a left and right part of the brain. It's not a specific area of the brain. It's not the primary sensory field which is affected, but these are areas which integrate information. Though it's a resting state activity network, which is basically here to integrate information. If you look at primary visual or auditory networks, activity is pretty similar. So there is not a lot of change in activity in primary auditory or visual networks, but the main difference is in integrating resting activity or integrating networks over the brain. Now, this has been shown in activation studies with fMRI. At about the same time, we performed the study in volunteers with Propofol TCI, very similar concept. In addition to fMRI, we measured EEG, which means surface electrical activity, and we found comparable changes in default network activity, which is the integrating part of the network. So the default network goes very much down during loss of consciousness, whereas the primary visual and primary auditory network remain stable in the activity. So it seems that you do not sort of abolish reaction, primary reaction to sensory stimuli, but you abolish the capability of the brain to integrate this information. So the default network and the loss of functional connectivity in the default network seems to play a key issue for loss of consciousness. Simultaneously, we looked at the EEG data and we applied a specific method called symbolic transfer entropy. Symbolic transfer entropy does sort of a normalization to the EEG, so it's basically seeing the looks at the EEG as a number of changes in direction, and you induce symbols for that, and you can do this with one channel, or you can do this with more than one EEG channel. Now, given that the EEG is a common Markov process, which is gives you the ability to predict what will happen in the EEG based on what has happened to this point. So looking at the past, you can predict what will be in the future in the EEG activity. You can calculate this future behavior of EEG, and then you compare it to the observation, what really happens to the EEG. And you will find a difference. Now, you can calculate the future of EEG activity not only by for one channel, but for more channels. And then you have to look at the difference between predicted and actually occurring activity. And you can take the other channels into account, how much information from another channel is required to influence the predicted EEG in such a way that the actual EEG occurs, which allows you to analyze the information that was contributed by another EEG channel. Knowing where these EEG channels are derived from, this method allows us to obtain information, how much information from different areas of the cortex are transferred to other areas to produce this electrical signal. Now, basically, this is effective connectivity, what you analyze with this. So it's not functional connectivity, which areas of the brain are active at the same time. It gives you information how much information is transferred from one area of the brain to the other. And we found a very distinct change and very characteristic change during loss of consciousness. There is a loss of frontal posterior information transfer. Given that we know the information flow over the brain, over the cortex, to the primary sensory fields, from there to the front, and then closing the loop as a feedback activity to the back, we found that a disruption of this last step is the key issue or the key characteristics during Propofol-induced loss of consciousness. So there is a decrease of frontoparietal activity, fronto-occipital and frontotemporal information transfer. This has not only been shown by us, it's also been shown by the group from George Mashour in 18 patients undergoing surgery under general anesthesia, and they were looking at propofol, sevoflurane, and found these differences in effective connectivity using two different mathematical approaches, basically same results. There is this loss of information transfer from the front of the brain to the back of the brain, of the cortex, during loss of consciousness, and basically it returns during regain of consciousness after anesthesia. Now this was for propofol, this was for volatiles. The interesting part of it came when they analyzed ketamine, and they compared it to propofol and sevoflurane. They were looking at loss of responsiveness to command and analyzed EEG frequencies in a more traditional manner, and also the frontoparietal feed-forward and feedback activity. If you look at delta, theta, alpha, beta, gamma activity, classical frequency spectrum analysis, you see these difference. You see similarities between propofol and sevoflurane with loss of consciousness. There is a, shown as the gray bar here, you see this increase of delta activity, increase of theta activity, and a reduction of fast EEG activity with both propofol and sevoflurane. However, this is entirely different for ketamine, where you see an increase in very fast EEG gamma activity and a decrease in alpha activity. So this is why frequency-based parameters have so difficulties capturing ketamine effects. And the interesting part of it, if you look at the frontal-parietal communication and information transfer, the picture looks very, very similar. So what you see at the top is feedback activity and feed-forward activity, feedback in red, feed-forward in blue. And there is this dramatic decrease of feedback activity no matter whether it's ketamine, propofol, or sevoflurane. So it's a common feature, even if frequency characteristics of the EEG are entirely different, the information transfer is very similar, or the change in information transfer during loss of consciousness. We tried to validate this study in terms of EEG activity in the fMRI, and this is very recent data. 16 volunteers, sevoflurane induction in the fMRI or in the MRI. We increased concentrations of sevoflurane until burst suppression, and then we reduced it 3% and 2%, and we measured simultaneously fMRI and EEG. So this is basically a quite rapid induction of anesthesia at time loss of consciousness. It was slowly stepwise increased to capture the moment where volunteers lost consciousness. Then we increased, put an LMA in, and decreased concentrations until regain of consciousness in these volunteers. And we found changes which were in general activity. So there is a general decrease of EEG activity, and there is a specific pattern of information transfer as shown here, and it's basically at loss of consciousness a very similar pattern as observed in the propofol group. And you see that frontal networks and parietal networks activity get really disconnected again during loss of consciousness. There is a disruption of connection to the thalamus. And what we found using different levels of anesthetic concentrations, that it's not really a linear function, that there is a minor blockade which increases after all. There is a specific pattern, or there are the specific areas of the brain which are in a stepwise manner altered. So as a first step, there is a change of within and between connectivity, and this pattern is really changing at a first step during loss of consciousness, and then the within connectivity changes as well until at burst suppression and high concentrations there is only regional activity maintained. So as a first step, the wider range connectivity is disrupted, and in higher concentration even the closer to each other localized areas are also disrupted. So there is a cascade of different responses, and these responses define the level of general anesthesia. It's not really a linear thing, and therefore it has been suggested to see anesthesia as a switchboard. and not as a submarine. So we do not go into different levels or depths of anesthesia, even if the concentration changes suggests this. There are different distinct areas of the brain which are altered in their function depending on different concentrations of anesthetics. And it's important to identify the brain mechanisms underlying different switches. And we are just there where we have identified most likely the switch for consciousness, unconsciousness, but there is a long road to define more of these switches. Then we have to find parameters which reflect the brain activity, underlying mechanisms, and as an ultimate goal, we have to take this into a cascade again in such a way that we can use it in a clinical way, and to have this cascade defining different levels of parameters. So I think at the moment we can, with quite good data, analyze what happens at loss and return of consciousness. At deeper levels, we are just at the beginning. There are some experimental data, but these have to come up to be analyzed in volunteers and patients, and then we will end up with a cascade and different levels of anesthesia rather than a continuum as we see it at the moment. Thank you.
Thank you very much, Gerhard, for this excellent lecture. Are there questions from the audience? Yes, Dr. Jensen. I come to the back.
Thank you for an excellent presentation, Gerhard. My question is, so in your combined model, where you have EEG, you have drugs concentrations, do you have a function which distinguishes if your inputs are giving different indications? Your EEG could indicate that the patient is awake, while your Propofol concentration might indicate that the patient is deep asleep. That should give you some possibility in terms of alarm mechanisms, or I don't know if that's something you have included in your model.
No, that's not included in the mathematical model. Has a weighting of parameters in it. So there is a model that overrules certain parameters. It does not give an alarm. So we tried to build it in that way, or it was constructed in a way that it provides a result without giving the information. But I think it's a very, very interesting approach, and we are currently going into deep learning approaches with this, and I think it's important to give a feedback to the user, because that if we try to integrate such a lot of data, if you do it from a clinical point of view, you will always overrule certain information, but this overruling, and I agree with that, should not be just done automatically without informing the clinical anesthesiologist. That's something that needs to be added in the future.
Thank you.
There's one more over here.
So,
Go ahead. One quick question following what he's saying. So in that model with the multiple parameters, have you done any, or does your model allow you to do a sensitivity analysis so you could see which of the additional parameters, in addition to the EEG, is most critical in correcting those shortcomings of the EEG?
Yeah. It allows to a certain degree, but the method that we used so far doesn't allow it precisely, and that's why we go to deep learning algorithms.
Thank you.
Question over there.
I think this is quick. Before Aspect got bought out, they were doing studies to look at variability in the BIS to give an indication of analgesia. So you could have a hypnosis and an analgesia indicator. Are you thinking about an analgesia, a method to detect analgesia to help me decide whether to give more propofol or more fentanyl?
There have been some data out just recently which tried such a multi-parameter approach to provide information about the level of anesthesia as well. I think EG alone won't be sufficient, but integration of a lot of data may help with that as well.
I have a question over there.
Yes, you are addressing the problem excellently. And everything is about what we want to know. We try to measure something, which means that we will assign a scalar value to something. But what is that something? And the question is illustrated by the fact, can we have unconsciousness with recall? Yes, ketamine. You remember the hallucinations. And my conclusion is that we, in fact, have not yet defined what anesthesia is. And thus we assign a number to what do we want to know?
I appreciate that comment, and I totally agree with that, which makes it hard to speak in front of so many people talking about automated anesthesia and concentration effect relation, because in our minds it may be easier to assume that anesthesia is just based on a concentration effect relationship with this stepwise related to each other. I think it's a too simplistic view.
The brain function is described in neuroscience, and it is commonly accepted worldwide that it is a connectome, which means that intelligent activity is a functorial process.
And that's basically what I try
That's
to,
the
yeah.
explanation of everything. But
Yeah.
this is all very complicated.
We have to move on. I allow just a few more questions, then we have the lunch break. Yeah. Otherwise, we will miss our lunch break. Please go on.
Just a quick question, Gerhard. What do we know about nitrous oxide and its effects on connectivity? Does it look like ketamine, or is it?
There are no data on that.
No one's
so
looking
far.
at nitrous oxide
not
anymore,
in
are
the not in the fMRI.
Yeah.
There are some data on electrical activity, and that looks quite similar.
Right.
Just a quick practical matter then, if we're looking for connectivity frontal to parietal, then an electrode set that just goes across the front, not going to do it. Is that what you're saying?
Basically, it won't capture that. The question is whether it's reflected by electrodes there. There may be. I mean, there is some data that if you use a permutation entropy at the front, the results are very similar. So you're not directly capturing the effect, but you sort of capture the results of this effect. At some point, I would suggest we need a parietal, but that's open for discussion.
Can I just add one fast comment?
Final question for
Yeah,
lunch.
because I want to defend the pharmacologists here in the room, like Mike and myself. We are using changes in the EEG indeed in a continuous way, but we don't use it to measure loss of consciousness or unconsciousness, but to measure a cerebral drug effect, which is a total other paradigm. And of course, you measure one channel, and that one EEG channel is changing gradually. And we'll just look to a drug effect, so which is another concept than looking to physiological changes in the brain like consciousness or unconsciousness. That was just a comment.
Assuming that this drug effect is linear.
Yeah, but we can go on.
I cannot prove that it's not.
Yeah.
I mean, it's
Yeah.
just that's an assumption behind it. I can appreciate that, and I can live
Yeah.
with that. We all
You can live with that.
clinically very well.
Then I think we can go for lunch. Jan, take it over.
Yeah, please go for lunch.
Thank you, Gerhard.